Good morning, ladies and gentlemen. So we are about a half of our course. Sorry, I have forgotten to share you my slides. We are about a half in the course, and from today we will have yet another change of the topic. We will talk today about superconductivity. Why is it so? Why did we change the topic? Because in next lecture we will combine Coulomb blockade, which we have learned, and Josephson effect to come to realization of quantum mechanics to artificial atoms, which one can make in superconducting structures. Let us see. All right, so you can see my screen now. We will talk specifically about the superconductivity, which is interesting topic, especially in quantum transport. So I will talk a bit about superconductivity in general, like I did in the course of advanced quantum mechanics, but it won't be most important. If you are in quantum transport, you only need to learn a couple of essentials of superconductivity. Owing to universality of quantum transport, which we have noticed, again, it doesn't depend whether superconductor made of niobium or wood or anything. Quantum transport depends only on few parameters, and we will see that now. Good. Many topics again with this superconducting topic. We will talk at large at Andreev reflection, which is the basis of all other effects related to superconductivity. And what will be important for us to arrive to supercurrent between two superconducting leads, understanding that as Andreev bound states. And that will bring us to Josephson effect, and we talk a little bit about manifestations of Josephson effects. So quite a structure, at least 4 steps. Good, so let me talk about superconductivity. You both attend advanced quantum transport, so I don't want to talk all the jokes which I usually do. So to remind, it is experimental discovery which didn't have theoretical explanation for many years. When theoretical explanation has come, that was very unusual by that time. Theoretical explanation is only consistent with the fact that superconductor is in a macroscopic quantum state. So it's intensity of superconductivity. It's not a scalar. It is eventually a complex number which has a phase, and that phase is of a quantum mechanical origin. But nevertheless, let me state all peculiarities of superconductivity. It has been discovered in a spectacular way as a vanishing of resistance in macroscopic samples. Right. We will see in a while that it's also a property of contacts. Right. So contacts between two superconducting leads have no resistance. Good. Another property is a Meissner effect. It is repulsion of magnetic field from the superconductor. Both effects are derived from the fact that superconductors can have persistent currents. Electric currents which are not accompanied by dissipation, which are the property of the ground state of superconductor. Right, and it is a phase which eventually provides the possibility of these currents. Currents are related to the gradients of the phase. If phase is constant, ground state energy of a superconductor does not depend on this phase. If phase is slightly varying, this gives us a state of low energy because it varies slightly. And in this state, we can have superconducting currents associated with the gradients of the phase. All right, that's what we want to know. Oh yeah, I've forgotten about simple cartoonish mechanism of superconductivity. In advanced quantum transport, we have seen that it is very cartoonish, but that cartoon works well if you want to describe peculiarities of quantum transport. So we accept this. What is a cartoon? That electrons, eventually, am I recording? Okay, I'm recording. It involves Cooper pairs. So cartoon says that due to attractive interaction, electrons form Cooper pairs, but it's not like single Cooper pairs flying in the metal. Since Cooper pairs are bosons, they form condensate. Macroscopic number of Cooper pairs goes to the lowest level, and it is the resulting condensate rather than single Cooper pairs, which provides this property of superconductor. What will be important for us that if you try to change the properties of this condensate, you still put a Cooper pair there or extract a Cooper pair. Yes?
So in 2D, we can have Bose-Einstein condensate. So in 2D, do we not have superconductivity?
Yes, in fact, in principle, formally, it is the fact at any finite temperature in 2D, this superconducting order is destroyed. In practice, our parameters are such that it would lead to finite resistance only for very, very large films, like perhaps 1 meter long. So as far as realistic two-dimensional superconductors are concerned, it is a rather academic statement. But formally it is correct. Right, so that again comes about spontaneous breaking of gauge invariance. And gauge invariance has all to do with charge conservation. Again, that gives us a hint that the phase can produce something electric currents. Good, that were properties of superconductors. Do you have any questions? Are you curious about this? Such many things one can study in superconductors, like penetration of magnetic field, which vortices, all that stuff. But let us concentrate on quantum transport. Things which will happen in quantum transport are perhaps simpler, but as far as I'm concerned, are more interesting. So what we want to learn from microscopic theory of superconductivity is the spectrum for charge excitations over superconductor. First of all, let us understand the charge excitations in normal matter. Right, so those are not electrons, as it would have been convenient to think. Rather, they are isoelectrons or holes. So you could add a particle in empty state of normal metal, then we have electron excitation, or you could extract a particle from field states using Fermi energy, and one can have whole branches. Very good. So what I plotted here in the left plot, on vertical axis is the energy of excitation, and on horizontal axis is the energy difference from Fermi energy. So if the energy difference is negative, we are talking about the state within Fermi sphere, and it needs electron needs to be extracted to excite the state. So negative E correspond to whole branch. Very good. What happens in superconductors? How spectrum is modified? Again, I wanna tell this to you at a cartoon level, right? What is a cartoon? We have a condensate, and energies of all Cooper pairs in this condensate are the same, which means it costs no energy, no dissipation to add a Cooper pair to condensate or extract a Cooper pair from condensate. Very good. If there's no dissipation, we have a chance to form coherent state. Right? So let us start, for instance, with a hole, and let us extract a Cooper pair from condensate. We will get electron state. Let us start with electron state and put the Cooper pair to condensate. We got a whole state. So electron and whole states in superconductors are mixed. And as a result of this mixing, the charge excitations are mixtures, superpositions of electron and hole. Right, the intensity of the superposition does depend on the energy E right at hemisphere. So these excitations, quasi-particles, are just equal superpositions. Right, with 50% chance they're electrons and 50% chance they're holes. But if you go to more negative energies, it becomes more hole-like. If you go to positive energies, it becomes more like an electron. And okay, it is virtually important for all our considerations that the resulting spectrum does have a gap. It has a gap which is related to intensity of superconductivity, to order parameter of superconductivity, which is called delta. Right, so we conclude that there are no charged excitations below energy delta. So one could wonder, the situation is actually similar to that in semiconductor. So why there was charge transport in superconductors at all? Yes, you can answer this.
The Cooper pairs themselves to make the...
Very good. Yes, the condensate itself provides supercurrent, but it requires quite some energy to organize particle current in superconductors. All right, so we go to Andreev reflections and reflection, and as many phenomenon quantum transport, it is best represented as a sort of paradox. So let us try to formulate a paradox. We consider a structure which has two sides, two big electrodes. On the left, we have normal material, and on the right is superconductor. And I have sketched the spectra in both regions. Let us connect them with a nanostructure, and let me take a nanostructure which provides no reflection for electrons. It can be a quantum point contact or just interface between these two metals without potential barrier. So it is convenient for me in this case to get rid of electron reflection. Then what happens is rather paradoxical. Suppose we have an electron come into the nanostructure, come into the interface, and the energy of this electron is smaller than delta. Right, since this energy is not available in superconductor, it cannot go there. Energy should be conserved. All right, we could say it is reflected, but it cannot reflect because nothing can reflect this electron. Nothing can change the direction of its momentum. Right, so that is a paradox of Andreev reflection, and it is this paradox has a simple answer. If an electron under these conditions enters a superconductor, it eventually adds a Cooper pair to it. That's possible, that costs no energy. To compensate the charge, a hole will go in opposite direction. A hole will be returned to normal metal. Fine, so it is kind of a little bit like a sale slogan. Actually, we send one electron, but we get two charges transferred. So like in shops, they say that they will give you 10 cents for the price of one. Good. So let us check whether this process is feasible from the point of view of conservation laws. We know that quantum mechanics is very democratic, libertanic theory where everything is allowed, provided it is not forbidden by fundamental laws, right? So let's see, the energy of this process is conserved, the same energy in the beginning and in the end. Holes has the same energies in Lectrure. Charge is conserved because charge is given to the condensate of Cooper pairs. Momentum is also conserved. It's a bit counterintuitive because hole gets the opposite direction, but it is so that electrons are kind of opposite some holes. A hole can be regarded as an electron moving in opposite direction, so it has the same momentum. Conservation of spin is also present. So both, if initial electron carries spin up, resulting hole will also carry spin up. That is because, I haven't mentioned it explicitly. Cooper pairs are singlets, spin singlets. They are made of electrons of opposite spin. Fine, so we learn about Andreev reflection. So how do I go fast today? Try to break me if I go too fast. Right. Let me talk more about this. So for 90% of application of Andreev reflections, we can forget about microscopic pictures of that, but let us also sketch a microscopic picture, and let me make a link to something which I told you about in a very vague fashion. Let me make it concrete. So what would be wave function of this excitation? Since we can have linear superpositions of electrons and holes, this wave function necessarily should have two components: electron component and hole component. There's also spin in addition, but let me forget about spin for a while. These two components wave function satisfies an equation which is analogous to Schrödinger equation, which is called Bogoliubov-Dijon equation. What is the structure of this equation? It's easier to comprehend. So the electron component and hole component, and the electrons are governed by usual Hamiltonian-like string equation. That Hamiltonian incorporates a spectrum and potential, boundaries, everything. For the holes, since they kind of time reverted, this Hamiltonian changes sign. But in principle, the same equation for holes. As to superconductivity, as we learned, it converts electrons to holes and backwards, right? That's why the fact of superconductivity should be there in non-diagonal blocks of this big matrix. Fine, that is Bogoliubov-Deged equation. If we consider a system like this, so there's a superconductivity on the one side. If we look at the solutions of these equations in normal metal, those are superpositions of, say, incoming electrons and reflected holes. I kind of visualized here a wave function in terms of electron and hole trajectories. Suppose I have a source of electrons, somewhere normal metal, and there are also some impurities in normal metal. If electrons come from the source, they could scatter quite a bit like like light is scattered in mist. But sooner or later, this electron would hit the surface of superconductor. There, it will be converted into hole, and that electron hole will move in opposite direction. We call this retroreflection. Moreover, it will go back absorbing the phase accumulated when electron moves along this trajectory. Which means that all scattering processes will be time reverted. So for any electron trajectory, whatever complex it is, there's precisely the same whole trajectory, which brings everything back. That's why electrons which are emitted from the source, which are scattered, do not fade away completely. Part of them, a part which goes to superconductor, comes back to the source again. Strangely enough, we expect them to be scattered, but they are focused back to the source. Right, that's how magic mirror can be realized with superconductors.
Can I ask a question?
Yeah.
I don't get the very first step where you conclude that we need a two-component wave function.
That discontinuous reasoning.
Oh yeah, okay.
Right, so the possibility to put a Cooper condensate and or extract, it provides mixing between electron and hole states.
And we cannot write that as just a weighted sum of two different wave vectors.
If we want to keep it quantum mechanical, It's really like a quantum mechanical superposition. It's not like in classics where we have chances to be there. It is a superposition. Fine. Something else that would I need from microscopic theory. Let me look at details of scattering, and I wanna use wave language. Till now, we just look at particles, right? The same can be formulated in terms of the waves. So there's a electron wave coming to superconductor. What will happen in superconductor? If energy is smaller than energy gap, it would not go, right? But what does it mean would not go? It is not so that it's quenched at very short distance. The distance at which excitation function can penetrate superconductors can be quite long. It is called superconducting coherence length. For realistic circumstances, it could be 100 and 1,000 nanometers, quite long. But anyway, it will be, the wave will be returned as a whole wave. Well, for particles, we don't have any parameter. We send one particle, another particle returns. For the waves, we have an extra parameter, which becomes important for us. We will have phase difference. We will have phase difference between electron wave, which is sent, and whole wave, which comes back. Right, this phase difference picks up the phase of superconductor. It is easy to believe. It also requires a very specific energy dependence. I would not kind of elaborated it. It's enough to know at the moment that there's universal energy dependence for energies within superconducting gap. Okay, that's basically all which we need to know in quantum transport about microscopic details of superconductivity. All right. Let me now formulate a little bit more extended problem. Let me understand the combination where the nanostructure connecting a normal metal and superconductor is not ideal. There's also a chance for normal reflection. So we look at combination of Andreev and normal reflection. Good, so what do we have here? We have incident electron wave. And it can be reflected as an electron with amplitude Rn, and it can be reflected as a whole with amplitude Ra. Good. If you consider the situation as a transport channel where some electrons are coming from the left, we can compute the current in this channel. Right, per electron coming. So if we forget about Andreev reflection, this current would be transmission coefficient 1 minus Rn squared. Right? It's a current per energy interval divided by conductance quantity. Good. Control question. What do I have to add to describe Andreev reflection?
Modulus RA squared.
Yes. With which sign?
Plus sign.
Plus sign. So how do you know?
Well, the Andreev reflection adds to the current. Because an opposite charge goes in a different direction.
Yeah. This contribution of holes and electrons are opposite in sign as far as current is concerned. Very good. So a little bit more complex question. How to simplify this formula in terms if energies are within the gap. Oh, you don't. You're just a little bit confused. It's sure that electron, if its energy lower than the gap, cannot transmit. Which means that the sum of the square roots, module squared, sum of the square roots is 1. One can express current in terms of Andreev reflection. And the answer is?
Minus Rn squared equals Ra squared minus 1, so 2 Ra squared.
Yeah. Rather strange formula which you associate current with transmission. Now it is related to reflection amplitude. Fine. That's a bit ahead of time. But anyway, let us go for a while. Nanostructure. We want to do the following. We want to combine something which we know. A scatter nanostructure is a scatter and superconductor. One can easily imagine that it models eventually any nanostructure made of normal and superconducting leads, because any scattering which can happen can be incorporated into scattering matrix. Scattering matrix for electrons. Let us see. Let me, again, it doesn't matter much whether we consider menu or one channel. One can always consider channels separately. So let me concentrate on a single channel. Scattering matrix for electrons. Well, let us have general expression for this. One channel matrices, two reflection coefficients. The moduli are the same, but the phases can differ. Transmission amplitude. Wow, I'm really scared. Transmission amplitude, which is the same for electrons going from the left to the right and in opposite direction, or into time reversal symmetry. Let us assume this. What will happen to the scattering matrix for holes? Right, since holes are kind of time reflected with respect to electrons, and time reversion and Schrödinger equation is expressed by complex conjugation, the corresponding amplitudes for holes would be just complex conjugated on that of electrons. Right. What does it mean in simple terms? Well, suppose that's what we already discussed. Suppose I have simple scattering matrix, which is just phase shift, which is accumulated, for instance, somewhere here. A hole which will return and make this pass will cancel this completely, which means that the phase vector is complex conjugated to that of electron. Right, so we also need André phase. Here it is. For electrons and holes, it has different superconducting phase has different sign, while the energy-dependent phase remains the same. Okay, so now we know everything about elementary processes of scattering, and we can try to get the whole scattering amplitude in this nanostructure. Right here, I have drawn some possible elementary trajectories, elementary processes in the scattering. Very simple one. Electron is transmitted through nanostructure, is reflected from superconductor as a hole, and this hole gets through nanostructure. That's simple. One would imagine more complex process. Right, so electron is reflected from a superconductor. There's a hole going to normal metal, but it is reflected from the back side of the scatter. Good, it is reflected from back side of the scatter, so it goes back. It is reflected from superconductor as an electron, and this electron reflects once again from the back side, right? And it is coming back as a whole. Here I concentrate on trajectories which contribute to specific process to Andreev reflection. I could draw similar system of trajectories, for instance, from electron reflection, right? But since we could express the current in terms of Andreev reflection amplitude, it will suffice. All right, so I guess we'd better make a break at this point. 8-minute break. Yeah, there was a question of the cancellation of phase shifts is due to approximately same wave vectors of electrons and holes. Yeah, roughly. It's better to talk about. It's a bit complicated. So this compensation is exact if electrons and holes are precisely at Fermi energy, at zero energy. If they deviate a bit from Fermi energy, there is some phase difference proportional to this energy distance, which I don't want to take into account. Does it answer your question? So it's enough to know here that the compensation is exact for all energies precisely at Fermi level. Good. Let me stop the recording. All right, I'm back. Let us state again that now we know all amplitudes which are involved in this trajectory. For any trajectory of the kind, we can multiply amplitudes of corresponding reflection processes. And what we have to do for finding the total amplitude is to sum up over all these possibilities. So how we can do this? Okay, let us see what we have. Simplest trajectory, electron reflection, Andreev scattering, this phase theta, and the Hall reflection, which I have already said is a conjugate of electron reflection. Right, if we look at more complex trajectory, in the beginning it is the same. The same it is in the end, because for any trajectory of this kind, the electron has to transmit the scatter, and the hole in the, at the end of the process has to transmit it as well. Right? And there is a factor, that factor, which describes the bonds. Right. And again, I forgot to say that I assume that scattering doesn't depend on energy here. Okay, it's not very important, but simplifies a bit the answers. All right. So with that, we have R and R conjugated. This is just a reflection coefficient, not an amplitude, but coefficient. And T conjugated are collected into transmission coefficient. That's what we have. All right, we see that this depends on the phase of Andreev reflections, so that on the energy, amplitude of Andreev reflection will depend on energy in this situation. Let us again go to a limit, a simple limit to comprehend what happens. At zero energy, Both phases are just pi over 2. And that we can substitute here. And we have to square this amplitude, right? And this is the amplitude of, Andreev reflection coefficient. It's probability rather than amplitude. So it has a bit funny shape. First of all, it's proportional to t squared. Why is it so? Because it's in its simplest version, it involves, even for more complex trajectories, it involves two transmissions, for electron and for hole. So the result is proportional to t squared. And there's a funny denominator for this. Good. So let us understand. Okay, just let us do full proof check of this formula. Let us substitute ballistic junction. For ballistic junction, we know that chance of Andreev reflection is 100%. Okay, we substitute it here, and indeed it is 1. Okay, so the current conductance. Let me talk about the value which you can measure also in multi-channel situation about conductance of Andreev structure. Right, so as we have already derived, there's a coefficient of 2 Andreev reflection chance in each channel. We are talking about energies smaller than the gap. Right? So all electrons which we send in energy strip of the energy strip of the vis EV are reflected as holes with this particular chance. That gives us a resulting current, and that gives Andreev conductance. Fine. So using our formulas, we can express this conductance, and this is again funny, inspiring thing about quantum transport. In this form, it does not care about particular properties of superconductor. At any energy which is within the gap, the answer is expressed in terms of coefficients of normal scattering. For instance, we can switch off superconductivity. How we can do this? It's very simple. Just heat the system a bit. We have 2 normal leads. We can measure conductance. We can figure out what are transmission coefficients. We can use the same set of transmission coefficients to predict superconducting properties. Let's see what is the question in the chat. Yeah, how to we measure this conductance? We measure the conductance as usual. So we have electric circuit with 2 terminals. One is normal, another is superconductor. Then we apply voltage difference, and we measure the current in this circuit. Apply voltage, measure current. It's two-terminal circuit, so it's rather simple. Does it answer your question? R here is indeed reflection probability, but Andreev reflection probability. It's a probability for electron to return as a whole. As I said, it's a bit strange because current is associated with transmission. But in fact, Andreev reflection is a sort of transmission in disguise. Fine, good. Right, so let us analyze this Andreev conductance for different sets of transmission coefficients. First of all, it is a known result for tunnel junctions, which has been observed at very early stages of superconductivity, experimental research in superconductivity. Tunnel junction, what would be conductance for tunnel junction? Since all transmission coefficients for tunnel junctions are small, the result will be much, much smaller than the normal conductance. So if you compare conductances in normal and the superconducting case for tunnel junctions, we just see many orders of magnitude difference. Practically, tunnel junction is an insulator in superconducting state. As far as QPC is concerned, there is a coefficient of 2. With respect to normal conductance, you understand how does it come about. It is just this sale slogan, which really works in quantum transport. For each electron sent to nanostructure, we have 2 electrons transferred. Right. If you have a type of quantum conductor, you have a distribution of transmission coefficients. You can integrate the answer with this distribution, got the answer. And the funny detail that for diffusive conductor, which has low transmissions, which has high transmissions, and for high transmissions, we have more Andreev reflections. For lower transmissions, we have less Andreev reflection. For diffusive conductor, these effects compensate each other, and the conductance just stays the same in normal and superconducting state, which was a subject of spectacular experimental observation at some stage. Fine, that's about Andreev conductance. Let me talk about Josephson effect. And again, there will be a little bit complex trajectory. So first of all, I will talk about Josephson effect at phenomenological level without thinking of electrons going between superconducting leads. Then we will talk about Josephson effect in quantum transport, and we will understand it in terms of Andreev reflection from 2 superconductors. Then we get back to phenomenological description of Josephson effect, and we'll derive some simple conclusions about behavior of Josephson junction. All right. Josephson effect. Josephson, it's, well, as you could guess, it is a name. It was very bright student in Great Britain. He worked with Anderson. He was kind of established scientist by that time. He was at sabbatical in Oxford. And that Josephson guy just made really unbelievable progress in superconductivity, and well, it appeared in several decades that also in quantum transport, in our understanding of quantum properties at macroscopic level. All that has been made in a couple of weeks. Was a guy by that age, but by your age. You might know that in England they have a very strange educational system. So basically there's a chance that you can get your PhD in the age of 23. They go somewhere very fast. Fine. What were the results? They've been derived from complex formulas, but the essence can be formulated almost without formulas. Right, so we take two leads, and each is characterized by its own phase, and one can have different phases in these leads. And Josephson tells us that in this case, there is a supercurrent going from one lead to another lead, current without dissipation. Since all the parameters are periodic functions of each phase, this current must be periodic in this phase difference. Why is the difference? Because, well, superconducting currents basically are gradients of the phase. Here we have a kind of complicated realization of a gradient. That is one statement of Josephson. And it's called the Josephson effect. And the spectacular formula by Josephson, which looks kind of very wrong, and you have to be a really young person in order to come up with this. You have to know little to make such discoveries. This formula relates time derivative of superconducting phase and voltage applied to these two superconductors. And if constant voltage is applied, the phase difference appears to be linear function of time, constant derivative with respect to time. Right, so one can derive it from gauge invariance, which we use, so breaking of gauge invariance in superconductors are manifested as dependence of the phase on voltage. Good. Let us see why it is called AC Josephson effect. So it's a really unbelievable system if you think of it in usual electrotechnical terms. you've got an element, you apply constant voltage. As a result, you have AC current at certain frequency. So how does it come about? It's periodic function of phase, and the phase changes linearly. So you have current which is periodic in time. Right, and this frequency is set by this relation. Right, that was a great discovery, Josephson, which has been quickly confirmed experimentally. Here it is, well, rather rare case where materialists could be useful in superconductivity. They have predicted something which experimentalists didn't know before and could not even imagine. So let us see. I want to derive a relation which looks rather abstract, but it kind of gets very educative. Simple deviation, but perhaps it is a bit surprising if you didn't know it before. This is relation between Josephson current and Josephson energy. If you talk about electron currents in normal metals, there's absolutely no relation between current and energy. Current is accompanied by dissipation. Here, the current is a property of ground state. That's why it can be related to the energy of the ground state, namely to its phase-dependent part. Let me start with the answer. The current is proportional to the derivative of energy with respect to phase. And the proportionality coefficient just made of fundamental constants. Fine, so that if you didn't know about this in advance, it looks a bit striking. But again, as I said, there's very simple and constructive derivation of that. Don't we have the similar form for persistent current in disordered metal ring? Yeah, in fact, we have. We will discuss it a bit later when we talk about quantum dots. Shall I kind of deviate a bit and explain the difference in more detail? All right, so the remark was as follows. There's also persistent currents without dissipation in normal metal rings. So why one should care that the ring is superconducting? Why to pay attention to this? Okay, let me sketch first the ring. Could be normal or superconducting. Let's junction to be here. And indeed, in both cases, we formally do the following. We apply magnetic flux, which goes inside the ring, and have some energy which depends on this flux. We can relate it to persistent current. For normal metal ring, this current is there, but it persists only at very small lengths, which depends on temperature, which is affected by inelastic processes in normal metal. Sir, it is about several hundred nanometers where this ring, where normal ring can have measurable persistent current. As far as superconductors are concerned, the phase coherence along the ring is provided for free by the fact that the superconductor is by itself in macroscopic state, a quantum state. So the size of this loop, I don't know whether anybody make a corresponding experiment, but theoretically it could be 1 kilometer loop, or perhaps 1 light year loop. Right, so nothing would affect phase coherence at this stage. And although it's a loop similar to normal metal loop, we could forget about this, the fact that it has to be in a loop, and just concentrate on the junction. All right, that was a bit long answer. Perhaps it was a deviation from the topic. Are you satisfied with this? Okay. Right, so deviation. Again, it's a deviation from the mathematical, but it's so astonishingly simple that I think you will enjoy it. We change the phase adiabatically, which means very, very, very slow, to allow for no dissipation. What will be energy change per unit time for such a process? If we look at it from electrical point of view, it's just work which is made by voltage and current, I times V, power in electric circuits. Good, but the current in our case is a function of phase, and voltage, by virtue of Josephson relation, is a time derivative of the phase. So time derivative of energy is proportional to time derivative of the phase, right? Which means that the coefficient of proportionality just defines the derivative of energy with respect to the phase, right? So we substitute time-dependent phase here, differentiate with respect to time. This is what we got. So now we can associate these two terms. Since what we did, we have computed the time derivative of energy in two equivalent ways. So we come to this formula. Good, that means that we don't have to compute supercurrent separately. We could just compute energy, and that's it. Let us see how we compute energy. Now I go back to scattering theory, going to bit macroscopically. So we have two superconducting leads, and we set a scatterer to describe the nanostructure connected to the leads. Right, let us see, let me fix some energy, let me understand what are possible waves in the structure. Well, in principle, I could start with electron waves, which come to the nanostructure from the left, from the right. I see that they can be reflected from superconductor and come back as holes. They come back to nanostructure. They are scattered. So it means that there must be waves, whole waves, which go out. They again Andreev scatter and they return as normal electrons. So these 4 types of the waves, other electrons, holes from 2 sides going to nanostructure, going from nanostructure. They are related by scattering matrix, and this scattering matrix has 2 facets, right? So first of all, there is scattering matrix of nanostructure. Okay, it's detailed representation. I would rather put it in compact form like this. Do we understand what is going on? So it deals with electrons, and it takes incoming electrons and returns outgoing electrons. It's one block, and in another block, it does the same with holes. So it is scattered. Let me explicitly show what happens. So for instance, this is coming. It can go here and here on the right hand side, on the left side, either reflection or transmission. Reflection, transmission. Very good. And not to forget that there's also Andreev reflection. And that couples the waves like this. How can I draw it here? That comes, no, let's see, B. B comes and is reflected as A. The same here. All 4 electrons. All right, good. So we also put it into a matrix, and that relates. So, in the previous slide, there were waves coming to nanostructure. You do scattering matrix, you have waves which go out of nanostructure. Now we do the opposite. We relate waves which go out to the waves which come back to nanostructure. Right, this is a situation we didn't have before. We have closed loop of equations. Right. Those are waves going out of the structure, and they expressed in terms of the same wave which goes out of the structure. That will be product of these 2 scattered matrices, normal and Andreev reflection. So that looks strange, but one also has to understand that there's no incoming wave in this situation. Nothing comes from infinities, from the leads. So it is a localized state. It is a localized state, and as such, it can occur if we tune this scattering matrix to the situation where that product has a eigenvalue 1. If it has eigenvalue 1, we have a solution to this equation. Right? What is this tuning parameter? Now we recall that Andreev reflection amplitude does depend on energy. So there is at least a chance to satisfy this equation at certain energy. Right, and after some algebra, one can find the energy at which this happens. So if you just put an electron to the junction at this energy, it will be there forever. It will come to the localized state. Right. It's interesting to see the phase dependence of this energy. For any transmission coefficient, at 0 phase, this energy is somewhere at the level of delta, which means these excitations inside are not distinguishable from delocalized excitations above the gap level, bulk quasi-particles in superconductor. However, if we increase the phase, the energy gets lower and it gets more lower for more transparent channels. For ideal transmission, it just hits 0 at phase equals pi. Good. Now we have already a feeling there's energy which depends on phase. So it must be related to electric current. Good. So Josephson energy. And there's a little trick which might just easily slip your attention. You just memorize the result, but in fact, there's a bit some cheating, which I would do if I had just a little bit less time. So this answer which we have obtained, this is for excitation energy. That is how much do we have to pay in order to put extra quasi-particle into the junction. We are not interested in this in particular. We are interested in ground state energy. But the properties of superconductor are such, and in fact we have derived it we could have derived it on Monday 10 days ago, 12 days ago during advanced course of advanced quantum mechanics, when we talk about Bogoliubov-Dizhin equations, that the energy of excitations and ground state are related. And the energy of the ground states funny enough, I have seen very mature and successful physicists in superconductivity who miss this factor. And here there's a sum over all possible excitation energies. This 1/2 is a bit confusing, all right? If you want to think in simple terms, you would say the Bogolyubov-Dijon equation. It has positive energies. It also has solution at negative energies. And these solutions are energy symmetric. So for each solution with energy E, one would find solution with energy minus E. All right. So many people think that these states are just field. And therefore ground state has negative energy. That explains sign well. It doesn't explain this 1/2. But okay, that's why the cartoons can be sometimes very confusing, and at some stage one needs to do calculations whenever suffering it brings. Good, 1/2. 1/2, but we also have two spin directions. That's why many people are not aware of this 1/2, because it cancels with number of spin channels. Very good. With this, we finally come to ground state energy, not the whole part, because ground state energy also includes bulk energy of superconductors, which could be kilometers long. It's a ground state energy which depends on the phase difference, so that it comes from the region which is felt by both superconductors from the junction. Fine. So now we can write Josephson current. Here it is for different transmissions, so we just differentiate with respect to phase. At very low transmissions, well, I will show it the next formula, but very low transmissions, one can just forget about this term. And there are very simple sign dependence of the current. At high transmissions, it's different, and eventually at ideal transmission, it's rather sawtooth-like shape. Did you see a saw? It is periodic. So if I go on with the phase, it jumps here and goes like this. Right, that was Josephson current. Indeed, a kind of a charm of that we can compute it just only from scattering approach, just understanding transmission coefficients, the distribution for any nanostructure, for any black box. Okay, this is what I told about tunnel junction. This universal coefficient in front of this, which is just proportional to tunnel conductance of the structure. That we will see several times in the course. This is Josephson energy corresponding to the junction. We have minus sign here. What does it mean? It means that it has minimum at zero phase. Good. In remaining time, I will tell you which people understood um, almost immediately after Josephson discovery. It has a particular significance with respect to way of thinking. Because in this case, Josephson junction, which looks like a fancy object, requiring low temperatures, superconductors, something exotic, just becomes a part of a regular simple electric circuit. So it's indeed what in philosophy is called reduction. We can forget about many properties of superconductivity and just concentrate on electric properties of Josephson junction. Right? And that is simple to do. Let me consider circuit where Josephson junction is between two leads, but also this circuit has capacitance between two leads. And there could be resistance, which for instance closes the loop between two superconductors. Right. Having this model in hands, how we can proceed further, that's very automated way to proceed. Fortunately, people kind of have trained us in electric circuits sufficiently well. It's current conservation, so we bind the whole circuit with a current, and this current is a sum of the currents through elements. What are elements? Josephson junction, the phase, resistor, voltage at this resistor, capacitor, also there's a current through capacitor proportional to the time derivative of voltage at its ends. Right now we recall Josephson relation. Voltage becomes times the time derivative of the phase. And it's convenient to rescale the coefficients. There are too many of them. Capacitance leads to two derivative terms. Josephson energy leads to this term, sine phi, and resistor leads to this term. Good. So if this equation is derived by a mathematician, by your friend from double E department, I guess he or she would do derivation perfectly, but would stuck at this point. Equation is non-linear. It looks complex and cannot solve it by direct mathematical methods. However, we can have very simple physical analogy with this situation, and we have a very good understanding of what is going on. First of all, I wonder if you saw this device, perhaps in a museum. It is what your grandmothers used to apply every day, apply actually with the hands. So there were plates of profiled iron used to wash clothes. That was called washboard. I don't know. I guess one cannot buy it now. I guess it's you really have to go to a museum. Moreover, physicists by that time were attentive to the masses. They paid attention to the fact that you usually tilt washboard in order to wash your clothes. Right. So this provides you a potential energy profile, right, which has oscillatory part and also uniform tilt. Right. An equation which we have derived is an equation of a particle moving to this potential. Capacitive term corresponds to inertia of this particle, and the resistance corresponds to, dissipation, friction of this particle corresponds to dissipation in actual external resistor. So that was people, they were not young, but they were skillful enough with electric circuits. They have put forward this formalism shortly after Josephson discovery. All right, what would I need out of that? Just a simple conclusion in the end of this lesson. It all depends on the tilt of this potential, and tilt is proportional to the current applied to the circuit. If this current is smaller than critical value, then minima of tilted potential, there are minima of this tilted potential. So the system's adjacent junction just will stick in a single minimum with a constant phase. If phase is constant, there's no voltage. It is related to time derivative of the phase. So the superconducting current going through the junction, provided the current doesn't exceed critical one. If the current is above critical, look, there are no minima for this potential. A particle which moves in there just cannot stuck in a stationary point. It will have to move. It means that time derivative is not zero, so we have voltage across the junction. Good, let me finish at this point. If there are some final questions, I will be glad to answer. All right, very good. Thank you for your attention. Thank you, Zoom participants.